Well, hey folks, how y'all doing? Um, we're looking at day 14. Let me just remind you of a couple of things here. One is that you have a written homework that's due this week. If you have questions about the written homework, I do have office hours tomorrow over Zoom from 12 to 1. And I'd be glad to go over any questions that you might have over the written homework. There are 3 items on the written homework, but you're only turning in one of them. You'll turn in an answer to number 1. The other 2 are coding problems that we're going to work on again in the next written homework assignment. And so just hold on to your code right now and turn it all in with homework 4. So save 2 and 3 for homework 4. You'll need it for that. Okay. So let's go ahead and get started here. Last time we saw these 3 theorems. If alpha and beta are disjoint cycles in S sub n, then alpha beta is equal to beta alpha. In other words, disjoint cycles commute. That's interesting in a sense because most permutations do not commute, but disjoint cycles do. If sigma is any permutation S sub n, then we can break sigma down into a sequence of disjoint cycles. So sigma is equal to alpha 1, alpha 2, up through alpha k. And let alpha be a cycle in S sub n. Then there's a sequence of transpositions tau 1, tau 2, up through tau k, such that alpha is equal to the product of these transpositions. So all permutations can be broken down to cycles, and all cycles can be broken down to transpositions. So we've seen these theorems already, and we did some examples of breaking down permutations into cycles and then into transpositions. Let's move on. We've got a couple more theorems to get through today, and then on Wednesday we will start applying these theorems to cracking Enigma. All right. A new definition here. If we rewrite a permutation as a product of disjoint cycles, and we did this example on Friday, then if I write down the lengths of these cycles in descending order, 3, 3, 2, 1, in the form of a vector, this vector is called the cycle type of sigma. So the cycle type is an indication of how long the cycles are that this breaks down into. This permutation has cycle type 3, 3, 2, 1. Now, this is an obvious observation here, but 3 plus 3 plus 2 plus 1 is 9, and there were exactly 9 elements in the set being permuted here. That's not surprising. If we were looking at a permutation S sub n, the numbers in the vector have to add up to n. Where this is going to become applicable for us is that when we're talking about permuting the alphabet with 26 letters in it, there are 26 factorial possible permutations. That's a gigantic number. Excuse me. But only about 10 to the third cycle types, 2.4 times 10 to the third, 2,436 cycle types. And so if we're trying to identify this permutation against a machine that is very difficult to break, if we can narrow down the cycle type first, that will eliminate lots and lots of these possible permutations. And so instead of trying to brute force this number, if we can try to get something that will help us unlock this number, then we don't have to brute force quite so many permutations there. That's the idea. Okay? And a key to being able to do that involves what we call the conjugate of a permutation. The conjugate of sigma by alpha is this permutation alpha sigma alpha inverse. So let me talk about this notation for a moment here. If you have taken modern algebra, you've seen this a lot. But the idea here is that alpha inverse will permute the alphabet in some non-standard order that might help us understand what's going on. So permutes the alphabet. Maybe into an order that is determined by things that we know about the permutation. For example, if we know that the letter A goes to letter J, then maybe we want to look at an ordering of the alphabet in which A and J are side by side, for example. So we're permuting the alphabet from its standard order into a non-standard but identifiable order that is relevant to the problem we're trying to solve, and not just the arbitrary ABC order that is standard. So this is a permutation of the alphabet that is relevant to the problem we're trying to solve. So we're sorting the alphabet in a way that makes sense for what we're trying to work with. And then we want to see what sigma does inside that permutation. Sigma now operates on the permuted alphabet. And then alpha inverse, not alpha inverse, now it's just regular alpha, converts this permutation back to the standard alphabet, then undoes alpha inverse. So converts back to the standard ordering. So this is the idea that we're doing some kind of translation, and then we translate back, and then we're looking to see what the sigma does inside a translated system. Even if you haven't taken modern algebra, you have seen this in linear algebra when you studied diagonalization. When you saw the idea that A was PDP inverse for a diagonal matrix, you call this process diagonalization. P and P inverse were linear transformations. P inverse would transform the standard vectors I, J, and K, or whatever our standard vectors were, into vectors of a system in which this linear transformation was a diagonal matrix. And then we could see what the diagonal matrix did in this system. That was the idea. And diagonalization gave us some information about the eigenvalues and the eigenvectors of A. So we have seen this process before. We're now seeing it in a new context. So let's do a couple of examples here. We want to conjugate sigma by alpha. So we will put an alpha in front and an alpha inverse on the back. So alpha is 2, 3. Sigma is 1, 3, 2. Alpha inverse is just alpha going the other direction, which is 3, 2. Of course, that's the same thing as 2, 3. For 2 cycle or a transposition, the alpha inverse and alpha are the same thing. All right, so let's see what happens. If I start with a 1, nothing happens to a 1 here. Then this permutation changes a 1 to a 3. And then this permutation changes a 3 to a 2. And so 1 becomes a 2. And then what happens to 2? 2 immediately becomes a 3. Then 3 immediately changes it back to 2. and then 2 changes it back to a 3. So it bounces back between 2 and 3 a couple of times, but settles on 3. And then if we look at 3, this changes it to a 2, this changes it to a 1, and then the last permutation doesn't do anything with it. So we end up getting 1, 2, 3 instead of 1, 3, 2. All right. Oh, so now let's try conjugating sigma by this alpha. So we're going to do, again, alpha, sigma, alpha inverse. So alpha is 1, 6, 3, 4, 2, 5, 1, 4, 5, 2, 3, 6. And then we write alpha backwards. So this will be 5, 2, 4, 3, 6, 1. All right, and let's see what happens here. So let's start with the 1. So if we start with a 1, this permutation changes it to a 3. Nothing happens to a 3 until we get to this transformation, and that changes it to a 2. Then nothing happens to a 2 until we get to this transformation, and this cycle changes it to a 5, and then nothing else changes to 5. So 1 goes to 5. Okay, let's see what happens to 5. Nothing happens to 5 until we get to 5, 2, 4, in which case it changes to a 2. And then this changes 2 to a 3. And then this change, no, this doesn't do anything to 3. This changes 3 back to a 1. All right. So 5 goes back to 1. So then let's look at the next element here. Let's look at a 2. Nothing happens to a 2 yet. 5, 2, 4 changes 2 to a 4. Now I'm looking for something that changes a 4. 1, 4, 5 changes it to a 5. 4, 2, 5 changes it back to a 4. And then nothing happens to the 4. So we get a 4. So then 4 changes to a 5 here. The next thing that changes a 5 is this cycle that changes it to a 1. And then this changes a 1 to a 6. So then we get a 6. Oh, let's see. All right, let's see what happens to 6. 6 immediately changes to 1. The next time 1 changes is way over here. It becomes a 4. And then 4 becomes 2, and then nothing else happens to a 2. So that closes out a cycle. 3 is not accounted for. 3 had better end up going to itself, but let's find out. 3 goes to 6. This doesn't change a 6. It's a 1 cycle, so 6 just stays 6. So still nothing has happened. We go all the way to here, and 6 changes back to a 3. And so 3 does, in fact, go back to itself. All right. So we have calculated both of these conjugates. I wanted to show you a couple of observations. And we'll mention these observations on the next couple of slides. Conjugating did not change the cycle type. This had a cycle type of 3. This is still a cycle type of 3. This has a cycle type of 3, 2, 1. Cycle of 3, cycle of 2, cycle of 1. And this is also 3, 2, 1. A cycle of 3, a cycle of 2, cycle of 1. Remember, we always put these in descending order, even if we don't have them written that order. So conjugating doesn't affect the cycle type of a permutation. So that's one of the observations. is that if we're working with a conjugation, the cycle type won't change. Here's the other thing, is if I write, if sigma is equal to, let's say, x1, x2, up through xk, and I'm just going to write one cycle, but it could have other cycles as well, then alpha sigma alpha inverse, the conjugate of it, replaces x1 with sigma of x1 and replaces x2 with sigma of x2. It's not sigma, alpha. Sorry, that should be alpha. This should be an alpha. Through alpha of xk, and so on and so forth. And so all of this business, all of this work we did down here to work out the conjugate, we have a shortcut. So let's walk through the shortcut now. I know I'm going to have a 3 cycle here. This is 1, 3, 2. What does alpha do to a 1? Alpha doesn't do anything to a 1, so 1 stays the same. What does alpha do to a 3? Alpha changes a 3 to a 2, so the next element will be 2. And what does alpha do to 2? Alpha changes 2 to a 3, so the 3 stays the same. And that's the answer we get, but we didn't conjugate. We just replaced every element in sigma by whatever alpha did to that element. Okay? Let's try it on this one here. If I want to conjugate sigma here using the shortcut, I know I'm going to have a 3 cycle, followed by 2 cycle, followed by 1 cycle. So I now look at alpha. What does alpha do to a 1? It changes a 1 to a 6. What does alpha do to 4? It changes 4 to a 2. What does alpha do to a 5? It changes a 5 back to a 4. Now, what does alpha do to a 2? It changes 2 to a 5. What does alpha do to a 3? It changes a 3 to a 1. And what does alpha do to a 6? It changes 6 to 3. And I've written this differently than the answer we got here, but it's the same permutation. The elements 2, 4, and 6 cycle around. I've just written this with the 6 in the front this time, but 2 goes to 4, 4 goes to 6, 6 goes back to 2. The elements 1 and 5 switch places, and the element 3 stays exactly the same. And so we have a shortcut for doing conjugations. All right. Like I said, these are going to be mentioned on the next couple of slides. This is Theorem 4, that if I have sigma and alpha permutations, and sigma and alpha, sigma, alpha inverse have the same cycle type. So that's one of the things. The other way around is if I have 2 permutations that have the same cycle type, then I can find a permutation that if I conjugate by that permutation, I get the other permutation. So this is actually an if and only if statement. If I have a conjugate, it's the same cycle type, and if I have 2 permutations with the same cycle type, I can make it into a conjugate by finding the right alpha. All right, another definition. An involution is a permutation that undoes itself. If I do the same permutation twice, I get the original things back, the identity permutation. Okay? Another way of saying that is that sigma is equal to sigma inverse. A harder way of saying this, but this is correct, is that if I look at the cycle decomposition, the transpositions, it'll contain transpositions, which are 2 cycles, and fixed points, which are 1 cycles. In other words, the cycle type will have only 1s and 2s. this is important because the permutation has to undo itself. And if I have a cycle with more than 2 elements in it, I won't get back to my starting place. That is, if 1 became 2, then I do the permutation again, 2 becomes 3, but I don't get back to 1 in 2 steps. And so I can't have any permutations that are longer than two elements. So that's relates involutions to cycle types. We've seen this word before. When we did on homework 1, we were looking at involutions in the shift cipher, which keys, or this is the adjective form, involutory, that 0 and 13 were involutory keys. We're looking at a more general version of that problem. A permutation is an involution if repeating it cancels itself out. So somehow I messed up the numbering here. This here is correct theorem 4. This is theorem 5. I'm sorry about the mess up with the numbers. Let sigma and rho be 2 permutations in SN. Then we get the cycle composition of the permutation. We're using rho now instead of alpha, rho sigma, rho inverse, by replacing each cycle of sigma with the cycle rho alpha 1 through rho alpha k. This is the second thing that we talked about a couple of slides back. This is the shortcut for doing permutations. That if I want to conjugate sigma, I can replace x1, x2, all the way through xk with whatever. I'm still using alpha and not rho here, but that's okay. Here they're using rhos, and I don't know why. But we're replacing every element in this thing. And then following up, 2 permutations are conjugates if and only if they have the same cycle type. It's not just if they have the same cycle type, we have a permutation that'll conjugate it, but if and only if now. Okay? All right, so an involution, the cycle type contains only 1s and 2s. A proper involution the cycle type contains only 2s. It has no fixed points. So every element is being permuted, and no element is being permuted to itself. That's the idea. So S sub n is the product of exactly n over 2 transpositions. And that means that n has to be even for this to work, but we do have an even number of letters in the alphabet, so we're good. Okay? So in S6, this is an example of a proper involution. 1 and 5 switch places, 2 and 4 switch places, 3 and 6 switch places. If I repeat the permutation, then 1 and 5 switch back, 2 and 4 switch back, 3 and 6 switch back. So this is an example of a proper involution. We say its permutation is of matched cycle type if every cycle length occurs an even number of times. So this is matched cycle type because I have a cycle of length 3 and another cycle of length 3. So those match. And they have a cycle of 2, but I have another cycle of length 2, and it matches. So every cycle length occurs an even number of times. So I can have an odd cycle, but I have to have it match with a pair. So it's not saying the cycle lengths themselves are even. So we're about to connect these 2 categories, proper involutions and matched cycle type. This is theorem 6 now. I've got the numbers wrong. I'm sorry about that. But we're not going to call it theorem 6. We're going to call this Rejewski's theorem. And this is sort of the crown jewel of what happened in the cracking of Enigma here. Is A permutation is of matched cycle type if and only if it is the product of two proper involutions. So if I have a permutation that is of matched cycle type, it can be broken down into an involution followed by another involution. A proper involution followed by another proper involution. Okay, let's do an example of Rejewski's theorem here. We have this permutation, and it has a matched cycle type. These cycles have length 9, and there are 2 of those, and then 3, and there are 2 of those, and then 1, and there are 2 of those. That's the cycle type. And so we should be able to write this as a pair of proper involutions. So let's get started. What we're going to do first is we're going to write each match cycle each match cycle pair, one above the other, but we reverse the bottom one. So I'm going to write the D over the K. AXT goes over YGC. And BLFQ VEOUM goes over NRZI WSPJH. So let me mention at this stage, it does not matter which of these we put on top, as long as the one of them is going forwards and the other one's going backwards. And if we had more than 2 permutations of same type, say we had 4 permutations that all had, or 4 cycles that all had length 3, it doesn't matter whether I pair these 2 together and these 2 together, or if I pair, say, these 2 and these 2, or these 2 and these 2. I can pair them up however I want to. And so this first step is hard to mess up. And so, just you want to write up one cycle over the reverse of the other cycle. And now we're going to write the permutations, the involutions here. The first one's easy. Alpha, we're just going to go straight down. So D goes to K, A goes to Y, X goes to G, T goes to C, etc. So we get DK, AY, XG, TC, BN, LR, FZ, QI, VW, ES, OP, UJ, and MH. All right. And so now we'll go and do beta. Beta is a little bit trickier. And for a moment, I'm going to skip this first cycle because I want to show you what the pattern is. The pattern is going to go up and to the right. So Y is going to go to X. Then G is going to go to T. And then when we get to the end, we just wrap around and C goes back to A, which is what happens here with the K. It just kind of immediately wraps around and goes back to the D. So beta is up and to the right, N goes to L, R goes to F, Z goes to Q, I goes to V, W goes to E, S goes to O, P goes to U, J goes to M, and then H wraparounds back to B. All right. And when we're done, sigma is equal to beta alpha. Now we can check this. I don't want to check this for all 26 letters, but in the interest of doing this briefly, let's check a letter from one of the cycles that's on top. For example, does V go to E? Well, alpha takes V to W, and then beta takes W to E. So V does go to E. And then let's check one of the elements in the bottom permutation. Does W go to I? Well, W goes to V, and then V goes to I, and so W, in fact, does go to I. And if you check the other letters, you'll find they all go to the right place also. And so what we have here is a way of breaking up a permutation of matched cycle type into a product of two proper involutions. We will see on Wednesday how to apply that and how that helped us break the Enigma machine. Y'all take care. See you around.